now an assistant professor in Berkeley Institute for Theoretical Science. And he got his bachelor's degree from and the master's from Marcel. Yes. And also he was obtained at the University of Marcel and what is this?
UCT.
Oh. I guess I have to translate this. English version of this university. So he obtained his PhD in theoretical mathematical physics in 2000, and then became a postdoc in Germany, at the University of London, right? In Europe.
Yes.
In February this year, he joined the Wesley University and became an assistant professor. His research area is on gravity and the related questions. Let's welcome.
Thanks, Professor Wang, and the introduction. So today, I will present some topic about the effective action from loop quantum gravity. More precisely, the one-loop effective action from the coherent state path integral formulation of the loop quantum gravity. So this is a work in collaboration with Renata and Muxin. So Renata is a postdoc now in University of Erlangen, and Muxin is a professor in the United States. So let's start. So this will probably you have heard this many times. So we have a problem on quantum gravity. So why we have a problem on quantum gravity? So we start with the general relativity. So in general relativity, we know that we have a gravity theory, but the gravity is nothing else but the geometry. So everything is geometry, and any energy in space-time will make our space-time become curved. And this is encoded in the space-time curvature. And how this is curved is related by the Einstein equation, which relates energy or matter field to the space-time curvature. And currently, general relativity has passed all our local observational tests, including the solar system, but it's also passed many strong field tests, like for example, the picture, the image of the black hole from the event horizon telescope. And also we know we have recently the observational test from the radiative regime, like the gravitational wave. And currently, our best effective theory of the gravitational field. And also, mathematically, we have a theorem which called the Lovelock theorem, telling us that if we give some assumptions, the assumptions including the local theory and including with propagating only 2 degrees freedom, which correspond to the 2 polymerizations of gravitational wave. And Lovelock theorem tells us that in body, general relativity is unique up to some boundary topological field theory. And now you may ask why we need to go to beyond general relativity, because it looks nice. The problem is the black hole. And inside the black hole, there will be singularity. Singularity means curvature blows up at some point. So it's introduced infinity. And this is confirmed by mathematically confirmed by the singularity theorem, which proved by Penrose.
这个之前那个报告人不出来。
哦，
这是还批评。
Okay, yeah. Okay, let's continue. Yeah, so we know this GR suffers from singularity, and this means that general relativity is not a complete theory. And we want to make it complete. This brings the problem of quantum gravity. And you may ask, so, okay, so we know GR is not complete, but why we need quantum to help us to make it complete. It's a very simple idea. So we know quantum mechanics, we have the Heisenberg uncertainty principle. This is very simple, and after this uncertainty principle discovered, one naive question is to ask if we have a field theory. So this is quantum mechanics. If we have a field theory, can we measure the localization of the field theory very sharply? And this comes very later after the uncertainty principle is found. And so so at that moment, we already know the electromagnetic field, the Maxwell equation. And now one asks if we can have a sharp localization of the Maxwell field. Bohr is right, because now we have a very nice quantized theory of the electromagnetic, which is given by QED, and we can measure the sharp localization of the electromagnetic field.
But it's renormalized.
After renormalization, it's finite, yeah, but at that time, it only cares about localization for quantization of the field. Yeah. But you know, Landau is Landau. But actually, it's not wrong if we consider the gravity. The idea is very simple. In gravity, if we consider delta x, so the measure of the spatial localization in some finite distances, let's say L, and we know from the uncertainty principle, the momentum must be larger than h bar over L squared. So if this is a standard field theory, it's okay. But now if we combine the special relativity and the general relativity, why general relativity? Because now we know the mass is related to the energy. And if we have GR, this will produce a black hole. Because this momentum, high momentum implies a mass, and this will produce a black hole.
But when GR is taken into account, there's no conservation of momentum anymore. So it's like
that conservation when I mean,
there is no local conservation of momentum or energy.
Yeah.
So this is not a well-defined measure anymore.
But if you consider in this setup, we only consider rest. Sorry, not rest. But a particle where its mass can be ignored, and then the energy from the four vector conservation of the GR, the energy is just momentum.
You mean the global conservation?
It's not global conservation. This
But
is
the
just
momentum
special.
itself.
No, this is
Yeah, how do you define?
no, this is just a special relativity, just a particle.
Yeah. For special relativity is okay, but when GR is taken into account, like single particle states are not so well defined notion.
Well, but this is just you think classically of GR. So we don't think the vacuum state of gravity, because gravity does not have. I mean, it also have a conserved quantity to go to the boundary. Yeah. But if we think classically, so particle is a quantum, and we couple it through Einstein equation, and this will produce a black hole. And so if this L is smaller than the black hole radius, we cannot measure L anymore. That means we don't have a sharp localization, because everything is hidden by the black hole horizon, and we cannot measure it anymore. And when it will happen is precisely a length scale called Planck length. So this is a simple combination of three constants we know so far, and constant is because we measure them as constant. So it's h bar, but Newton's constant, which tells you how matter couples gravity and also the light speed. So this means basically we already go to a quantum regime, which L Planck is believed to be the smallest distance we can make. So this is why quantum gravity is important to realize to help to solve this singularity problem. And by the way, this is first found by the Bronston, which in 1930s, but I think it's largely unknown. So not so many people know he found this property. Okay. Now so if we look at the problem of quantum gravity, it's actually really hard. So that different approaches, the quantum field theory-based approach, like asymptotic safety or dynamical triangulation. And there are also canonical approach, which largely the most important approach is the loop quantum gravity, where loop quantum gravity also have a path integral approach, which is called spin-fold. And all these approaches, they have a shared principle, which is no perturbative. So they are no perturbative and they are background independent. I'll tell you why we need this two. So no perturbative because if we do it in the background field method, like the standard 12P, one finds that GR is not perturbatively renormalizable. Background independence is related to the fact that GR is a diffeomorphism invariant. It's the theory about our space-time itself. But there are some differences between these two approaches. The most important one is, okay, they are both background independent, but for asymptotic safety or dynamical triangulation, they rely on some background field structure. But for loop quantum gravity, we don't require any background structure. So we quantize the space-time at the beginning. Okay. Now the question is how to quantize them. So to quantize the theory, there are two main important questions. One is what are the states? What is our Hilbert state? Another question is which are the physical observables? And loop quantum gravity can approach these two questions. We have an approach which answers both of them through the so-called reduced phase-space approach. I'll introduce you later on. And after that, so this is the canonical quantization. And in this reduced phase-space approach, we have a physical Hamiltonian. And with the physical Hamiltonian, we can either define a phase-space path integral or coherent space path integral. And then we can go to the second estimate with the unit quantum field theory. So in this talk, I will tell you how to do this for this coherent state path integral. Okay, now this is the more technical. This is how we do the quantization. How we find the Hilbert space in loop quantum gravity in the reduced phase. So we start with the nicer formulation of GR. So GR has many formulations. They are equivalent classically, but some of them are nicer than the other formulation. So this is another one. The reason is the following. So there are two constraints, first of all, because GR is a completely constrained system because of the diffeomorphism. There are two constraints, but now we write them in a way which is very similar to the Yang scheme. Why one speaks F? F is the curvature term in Yang. It's exactly the same thing as the Yang. So A here is the SU2 connection. That's why it's very similar to SU2 Yang. Of course, the constraint, so this is the constraint, which is not like the Yang physical constraint. And also the form of the constraint is different with Yang. But in general, this is a theory of SU2 connection and SU2 electric field. So if we write AI in this way, at least we can go to a kinematic Hilbert space, which is very similar to the Yang space. We are no perturbative way. And also because we have SU2 connection, we have the SU2 dot constraint, which can answer the SU2 big environment. As I said, compared to the standard Yang theory, the difference is GR is the diffeomorphism environment. We have extra symmetries apart from the SU2 gauge theory. And this diffeomorphism environment here appears at both C and CG, they are constraints. They are not dynamic evaluation. And this is somehow called the problem of time, because in GR, C, this Hamiltonian is the constraint. So it doesn't generate the physical time resolution, it only generates a gauge transformation along time. And the problem of this is we cannot find any local strong observables in the theory. Because a strong observable means it's independent of the gauge. But time translation is the gauge is the gauge itself, which means the only observable we can find are the boundary charges. That's the only thing we have. So this is called the problem of time. And to solve the problem of time, we need to introduce a matter field. If we can introduce a matter field, we can solve this. And this is like the gauge fixing. And also, if you consider the Einstein's equation, if we don't have matter, Newton's constant is somehow trivial. It's just the overall parameter for our action. Only when we have matter field, Newton's constant becomes non-trivial. And this will later on, if one has a renormalization for pure gravity without matter, it's renormalizable at one. But when we have matter, it's not already. Not renormalizable at one because the Newton and the no trivial happen. Okay, so this is something related to matter. So we need to have matter. So we describe a gravity field because gravity tells us how matter changes the gravity. And with matter now, we can define the Dirac observables. Basically, what we can do is we parameterize the gravity variables with the values of matter field. So what this means is that we use matter field at our time and space coordinates. This is like the gauge fixing. So matter field is involved with in the space time, and then we control the trajectory of the matter field to find the time. The realization is very simple because when we have matter field, we can, so this constraint is complicated, but when we have matter field, we can linearize it. Linearize it means that the constraint is linear in the conjugate momenta to the matter. And when we have the constraint in this form, we can solve it easily because the constraint acting on the state equal to 0 transforms to the d phi acting on the state equal to h acting on the state. And this is nothing else than the Schrödinger equation. And here phi defines the time. This plays a role of time, the standard Schrödinger equation. So this is the Schrödinger picture. And if we are in the Heisenberg picture, this is related to the von Neumann algebra, the cross product of von Neumann algebra written by Wittmann and collaborators. So these two are somehow equivalent. And with this gauge fixing or parameterization of space and time, we now have an ordinary Hamiltonian system because now this HI becomes the physical Hamiltonian instead of constraint because we solve the constraint with matter. And with this, we have a physical Hamiltonian, and now it's really like a standard gauge theory instead of a constraint system. And then we can quantize the theory. So the quantization is realized on what's so-called the spin network space. And the Hilbert space is nothing else but because we have SU2 gauge theory. So the Hilbert space is just all functions on the SU2 group theory. And we have the Gauss constraint. So we have the gauge invariance on at each point with this SU2 group element B. So basically, this is realized on what we call the abstract graph. The abstract graph is a graph made by node and link. And this is just a graph, and the Hilbert space is on this graph. On each link, we have SU2 group element or functions of SU2 group element. And on each vertex, we have the Gauss constraint, which realized as SU2 invariance on each vertex. And this, so all these links, they become closed loops, which are gauge invariant observed. And when we quantize it, because these are all the SU2 representation theory, we can do the Fourier transform or the Peter-Weyl theory. And this becomes the SU2 spins on each link, and the gauge invariance becomes SU2 intertwiner on each node. So SU2 intertwiner means basically when we have different spins meet at a point, the total spin of this point is 0. That's the gauge invariance. So we don't have external spin charges. These are the SU2 gauge invariance. The last thing of this quantization is that we have now a direct explanation of geometric operators. Because if we go back to the formulation, what introduced these SU2 spins is the electric field. The electric field is here. The electric field here is nothing else but related to the area operator in the quantum gravity. So the area operator, if we act on the spin network state, is just gives to Earth G squared, or Gg plus 1, with LT squared. So here it automatically a quantized area for the state. And also it gives a quantized volume because volume will act on each node. So if we have a state like this, now we can translate it into a quantized space-time object. For example, because each spin corresponds to area and each node corresponds to a volume. So if we go to the door graph, the four-valence spin is nothing else than a figure. And each spin, each link here is the area of this triangle of the equation. And the volume operator acting on the interquantum state gives us the volume, quantized volume of this equation. So this is the basic building block of the theory. And then we can use the physical Hamiltonian. So if we give an initial value, we can evolve it using the quantum equation motion. That's the idea of the theory. Of course, the quantum equation motion, quantum Einstein equation is really complicated. That's why we want to go to the QFT approach to build the passive get the effective action. So if you already learned QFT, maybe you know this. In QFT, how we study things, usually we use the effective action. So effective action is the action right on some cutoff scale, because we know if we don't have a cutoff scale, we have infinity. We need to use the renormalization. And this is more or less the renormalization procedure. So we introduce a momenta cutoff. And if we go to UV, this means the momenta goes to infinity. If we go to RR, it means the momenta goes to 0 and the wavelength is infinity. So these are the two limits of the UV and RR. So right? But when we directly apply to PFT, we already know that, if we apply directly to gravity, we already know that gravity is the perturbation with no renormalization. But we have now no perturbation with the renormalization method, which is, for example, asymptotic safety. And if we write out the effective action, it can show that there are theories that if we go to the UV, they have a UV fixed point. That is what's called the asymptotic state. But if we start from the canonical approach, we know we have an effective approach which gives us the RR, which is basically classical gravity if we want. But to build up order by order, we need to use the perturbative asymptotic states. So these are both pro and con. Okay. And so if we start from full quantum gravity, using that the area spectrum is discretized, and we have discrete area spectrum, there is a very simple dimensional argument saying that we have UV finite order by order. Why we have this? So if we have a standard effective action, one can always write out the UV divergence of the effective action. If it's not renormalizable, because now we have a coupling constant, which is the RT, that's the Planck length. I introduced that at the beginning, so I use the capital L, this is the small L. And E is the energy cutoff of the momentum. And for general effective action, we have UV divergent when E goes to infinity up to infinity. But if we consider LQG, so that is I should put a comma because this was introduced actually by the geometry. And E, we know the energy scale is nothing else. In a lattice theory, is 2 pi over the lattice size. Because when we do the Fourier transform, if we have lattice size, we have energy momentum. We have a momentum cutoff. So this is so this energy cutoff is actually the lattice size cutoff. And now because in LQG, we know the area spectrum, this lattice size is discretized. It's proportional to the spin. And then we can rewrite out this effect action using the spin. And if we write out using the spin, one sees that it will finite order by order when spin is not zero. And we don't have spin zero because spin zero in our spectrum is zero. We don't have this. We start from spin 1/2. That's the minimal area. So when we have a minimal area, we see that the effect action is finite order by order. Yes?
Are you assuming that you are in some area eigenstate? Like
No,
what
it's,
conditions?
It's general, but this
So
is the
then
minimum.
what is the, for example, in quantum mechanics, you have different spin states.
Yeah.
So imposed, right? So
Yeah.
what is J0?
Yeah, but
Or superposition states?
it's okay. Doesn't matter. What here we are arguing is that it has a minimum value. Sometimes all these terms order by order are finite. It cannot go to because G0 cannot be 0.
Yeah, but I'm asking like for if I want for the errors.
Well, that's so effective action directly give you the expectation value.
Yes, but
But
what do you put it? What value do you put it to J0 for generic superpositions?
Doesn't matter. That's the value. It's just the value. We just want to show that it does not go to infinity or J0 does not go to 0. For generic state, it cannot go to 0. That's the value.
Yes, that's good. I'm not asking for that. That's okay.
Yeah.
I have confusion. It's even when I was in the business, from gravity, I never worked on renormalization. What I'm confused about is in usual QFT.
Yeah.
Okay. The renormalization, in fact, heavily depends on the fixed background. Even in non-abelian gauge theory, when the gauge field can take away energy, but because there's a fixed background, we can throw everything into a lump sum to renormalize. For example, quark. Okay, we can throw the gauge field and everything into quarks, and we do a renormalization because there's a fixed background where the energy for single particle states are well defined. But here, in quantum gravity, we cease to having a fixed background, and gravity certainly can take away energy. So when we say we take a momentum go to infinity in the usual renormalization scheme, I don't really know what it means. In gravity, we need a boundary, for example. Then we can define something like ATM mass or whatever. Those are well-defined conserved quantity. But in quantum gravity with matter,
Then we can define the total quantity.
yeah, but it's kind of overall thing, right?
No, it's not overall. Not because when we have matter, we can have no problem.
Yeah, but
So when we have matter,
but the background, like the spacetime is in general curved, right?
Yes.
So the local energy of a particle is not really well defined. Because gravity can always take away the energy because it has its own energy.
Well, it's always reflected from this. So the gravity energy is nothing from the SP.
Yeah, but we don't really have a fixed background.
Yeah.
With respect to the energies defined.
I mean, you need to define the quasi-local energy, that things which is the integration over some region. But this is the quasi-local motion.
Okay, so there is a notion of quasi-local.
Yeah. Yeah. Okay. Okay, so basically this is the idea. This is what I explained. Why is UV complete? Because it's different to the standard quantum field theory because the lattice space here now is given by this G0, but it's not physical. It's the dynamical quantity given by the expected value. It's something intrinsic in our theory, not what is given outside. So that's why we said so this discrete scale, which makes the theory UV complete, is determined by the dynamics of the state, of the dynamics of the theory. So it's an intrinsic property of the theory. And more precise, it will be given by the quantum equation motion. And I will make this precise later on. Okay, so this is more or less, I already gave you an overview. This is more or less how our procedure is now. A bit more technical. So we start with the warm up. What is the effectivity? As Ethan said, we start with background field method. This is how we start to proceed in field theory. So suppose we have a very simple scalar field action. And then we split between the classical background and the perturbation. So we have the classical background, which is called theta, and we have perturbation of the field, which is delta. And then I can write out the generating function now at one loop. So at one loop is just the background action plus the background forces, and now we have the determinant of Hessian from the perturbation. And this is why it's called one loop, because we consider only the one loop contribution of the perturbation. So it contributes as the determinant Hessian, the integral. It's an integral of the Gauss integral. Yeah. And here, if we look at the Hessian, what is Hessian? Is we write out that by explicitly it's d squared plus v double. And this is very simple. And how to define the effective action? Effective action is we go the Legendre transform. Somehow we regard I didn't write out W, sorry. But the effective action is nothing else but the classical action minus the log determinant. We write this into the action as well. And of course, if we want to compute high loops, we can compute high. This is only one. And this log determinant is the linear, the matrix formulation. Log determinant is nothing else. Twist log. So we can change the log and determinant to the twist log. And this will give us an effective action because we can combine this quantum correction to the original classic potential, because the kinetic term is the same. And then from this, we can compute the effective potential, which is nothing else coming from the twist log formulation. So twist becomes the integral in this data, because twist is the tracing all the Fourier mode. Tracing all the Fourier mode gives us the integral and the logarithm of the determinant Hessian of this. And this will introduce an effective action, and from the effective action, we can derive what is the equation motion with the scalar field is satisfied. And this is the one loop corrected quantum equation. And it's coming from the variational principle of the effective potential in these simple things. It needs to be zero if you do it correctly. And actually, this translates into the classical part, which is dv by plus quantum correction equal to zero. So we have the quantum correction to our classical equation motion. This is basically what we need to do for the quantum equation motion. And what it means is actually the expectation value of our scalar field at one, how it behaves. And okay. And now, if we consider gravity, we can do similar thing. Gravity is more complicated because if we go to high order terms, we need the Fourier mode is not well defined because everything depends on T. The background can depend on T. If background does not depend on T, we can do the standard free. If background depends on T, we need to go in the proper time, but this can be done in the external formulation. And what has been done is the following. So if we write out all the corrections, so if we factor out all the divergences at one loop, it turns out if there is no vector field, gravity at one loop is renormalizable. But if one goes to two loops, it's divergent. So one is everything is okay if we don't have matrix. And this is given by the following. So if you calculate the divergences from the effective action, basically we are counting the divergences for the effective action. And so there is the particle divergence. So this lambda UV is the UV cutoff. So if UV cutoff goes to infinity, we have a particle divergence. And this will contribute to the normalization of the cosmological constant if we add the contribute. And we have quadratic divergences, which will contribute to the normalization of the Newton cup the constant. And finally, we have the logarithm. This is more complicated, but if we go to unshare, which means we go to the classical, if we go to the solution of the Einstein equation, this term will go. It's not free. So it basically means if we go to unshare, gravity is renormalizable at one loop if there is no matter field. But if one go to two loops, one is immediately negative. Renormalizable, I mean.
Sorry.
Yeah.
So when you say you go to on shell, how much of your food is still on?
No, unshare means because it is backward. Unshare means unshare. Because everything we buy is the Yeah, one important thing is that this renormalization of the gravitational constant requires a lambda. So there is no cosmological constant in free. So we don't have a renormalization with the Newton's constant. There is no cosmological constant. Okay. And now I also need to introduce some notion of the coherent state possibility, because you may be familiar with the effective action in the standard field, but what it means by coherent state possibility. So basically, it's related to boundary condition when we calculate the effective action. So in QFT, usually we have an asymptotic boundary condition, which is the vacuum state. But if we consider not vacuum state, but some other boundary states, then we can go to the coherent state. So so precisely it can be understood as the following. So we can define phi zero, which is the vacuum state of the scalar field. And now we can define the perturbation, the differences between phi zero and the standard scalar field by a difference. And this difference is reflected as reflect the fact that we have different initial and boundary states. And in this way, we can define the effective action in terms of the coherent state, which is basically telling us what is their size.
Yeah. So I have two questions. The first question is, are you still, so in this slide, are you still talking about the standard field?
But with coherent state.
Okay, so coherent state means the coherent state
Incorrect.
field.
Yeah, obviously. How we coherent state compare. Yeah. And this delta phi, if you calculate in the diagram in Feynman, it's nothing else but the coherent state. Coherent state is not exactly value, but it's how this phi x take values on different boundaries. Basically, what is this delta? And this expectation value of the delta phi is now given by an effective action coming from the coherent state. And this is how to make sense of the coherent state effective action. And we can rewrite them as the standard effective action, which only writes them in asymptotic. This is basically we change the asymptotic boundary condition into the coherent state. Yeah.
So what's the finding here? Is that some matter field or related to space time?
No, this is just a scalar field, metric field.
And
Yeah, I didn't talk about gravity. So this is a standard gravity, but right the coherent state. The coherent state means you give it some value.
so what's the relationship between this phi field and the graph?
On quantum gravity, I'll take a similar thing as a field. So gravity later on, it will be similar to this static. So this is the warm up related into the standard effect. Because usually in gravity, we only deal with the asymptotic. Okay, yeah, now we go to the gravity part. Now go to the gravity. So as I said, we need a metric field. So we use a very simple system, which is gravity coupled to dust. And in this way, we can introduce a physical Hamiltonian, which is H, and we can also introduce a complex spiral coherent state to our quantum spacetime. And the coherent state has two parameters, as you know. One is the semi-classical parameter. For example, when this t goes to 0, we have the explicit with the classical state. So this t controls how the coherent state is t. So when t goes to 0, it's the sharp. And this G is the coherent state label. So it's basically a label in SL2 state because we have our spin network in SU2. So that's why this is called complex bias. So spin network in SU2 means our configuration space is SU2. But our fixed space is T star SU2, which is orthogonal to SL2 state. That's why it's complex bias. So basically, this SL2C group element encode all the information of our fixed space. Right. And basically, I mean, explain it in geometry means we have the shape and we have the shape of the quantum geometry and also the shape matrix of our. These are the two things explain the state. And with coherent state, we cannot define a transition amplitude like what we have done with quantum mechanics or QFT. So we have Hamiltonian, we write them at very small time steps. And we define the transition amplitude between two different boundary conditions. And now if one do it step by step, and this n is time steps, and we can write out an action from the coherent state. This is the coherent state amplitude. So we have the kinematic term from the overlap between different coherent states, and also we have the contribution from the matrix element. And this part is very complicated, but it can be done numerically. Okay, so this is just idea, and now we are realize it on a very simple configuration, which is the flat spacetime. So in the flat spacetime, we can use a graph which contains six links. And 6 links, if we go to the dual graph, it corresponds to a cubic geometry. So it's like we discretize somehow our spacetime as many cubes. Because we are in the flat spacetime, it means all six spaces of the cube, they are equal because of the homogeneous and isotropy. And this corresponds to a coherent state label in a very simple way, where each area is encoded in this P1. So what I call P is later on corresponding to the area that before, which is discretized. Of course, as I said, this is background. And now the perturbation is really neutral. And when I write all the perturbation on the background, so of course we have B, which is the perturbation variables of metric, and we have the increased curvature. And if we write all the perturbation in the flat background, the background does not depend on time, we can define the lattice Fourier transform. It's standard. And then I introduce a very small parameter mu, which is somehow the lattice coordinate length. This is not the, and it just tells us how many lattice points on this spacetime. This is very important when we define the lattice transform. And what is the long wavelength limit in this setup? It means our lattice point goes to infinity. That's the long wavelength limit. And now I can compute the hashing. It's complicated, but not that complicated. So the hashing is always like this because we are in a perturbation quadratic system. What we need to do is just to determine the determinant. To still remember the treatment of the log determinant system. So we need to have the determinant of the velocity. But this is just a block matrix along different K0 and K different momentum space. And this determinant turns out to be always in this form, if you want. So we have 6 different modes, if you want, because this is nothing else but the standard. So 1 over this is somehow the standard propagator appears in the classical system. But now it's not classical because it's determined by some complex numbers, and these are different complex numbers. So this is no trivial part. There are some special configurations we can write them explicitly. For general configurations, they are indeterminate numerically because it's too complicated. For some special configurations we have, for example, if we only have the momentum along one direction instead of the standard momentum along all directions. If we only have the momentum along one direction, we can write them simply as the 1 minus alpha over k squared to the square. So this is nothing else. If we recognize it's the tensor mode of the gravity. And now it's not the standard gravitational wave propagation. It's back directions because now we have sine and cosine. In the standard gravity, it's just 1 minus 1 alpha. It gets correct. And most things is, so in a continuum theory of the long wavelength limit, we have SO3 or SO3 rotation invariance of the propagation. But here we didn't have it because now we are in sample space-time lattice. But this is just the space-time lattice itself is given by the theory. But because of this space-time lattice, we don't have any SO3 invariance in the continuum limit. That's why this is the special configuration. Because in the classical theory, if we have this, in the continuum theory, if we have this, we have everything because of the SO3. But now we don't have it. This is a very simple thing. Yeah, this is what I said. Long wavelength limit when you cover the classical gravitational wave propagation. Yeah, and one can actually calculate all the propagation classical continuum. It turns out, so this is more or less we are checking the RR unit theory, if it's compatible with that. And it turns out it's compatible with here. And it's very nice because we recognize all the modes. If you look at this formula, we have 12 different terms, and these 12 different terms correspond to all these different modes. So we have 3 Gauss modes, which correspond to the SO2 Gauss constraint, and we have 2 vector modes, we have 2 tensor modes, and we have 2 scalar modes. These are all the modes that have theory with a metric. And if we look at the pulse, because in quantum field theory, the most important thing about a pulse data is the pulse. And if we look at the pulse, only tensor mode has no zero pulse. This is the only dynamic distribution. So that's why we recover gravitational waves in the R. And all the other 4 modes, so we still have vector and scalar. These 4 modes, they are just for moving mode. They have a trigger. This is because we define our dust as a reference frame, so they are not dynamic. Okay. And now we can even calculate the effective action on the long wavelength of motion, which is the effective action on the continuum. This can be done exactly because we have the determined n on the block part of the Hessian matrix explicitly in the long wavelength limit. And when we do this, we can use it's a very simple calculation similar to the quantum mechanics. And then we use the log determinant formula, and then we introduce the epsilon regularization as in the quantum field theory. We obtain the one loop effective action of long wavelength limit. So it's all in this form. So J0 is our boundary value, and all the others are determined the summing over these different modes. So these are what is the importance is here? This C number, this is the only number we need to determine, and it can be calculated exactly. And this number is the real number. What it turns out is that now, because we have this effective action, we can write out the quantum equation motion. And when we write out the quantum equation motion, we can try to find out what is the critical point, the solution of this quantum equation motion. And it turns out it gives a real solution. It's a very large number, but it's a real solution. for the quantum effective equation motion. And this is the for one loop calculation. Just we go to the non-wavelength loop, which is the continuum loop. So it's not classical anymore. That's why we see a critical point. Of course, you can. When wondering this is just long wavelength approximation. What happens if we go beyond the long wavelength approximation? And then everything becomes more complicated because we don't have the explicit formula. We need to calculate the numeric. So this is the propagator again, as I showed before. So one can still recognize all the physical modes because this part is the Gauss constraint, which are the 3-gauge modes. And this part are 6 physical modes. As we said before, we have 2 gravity plus 4 matter field. 2 gravity mode is dynamic for matter mode, not random. And then one can calculate this on different configurations. So long wavelength limit is this lattice point goes to infinity. And if we don't go to the long wavelength limit, one can do this numerically, and this is somehow the behavior of alpha on some fixed configuration. One say that we convert variable to a constant. And this part is already long wavelength, somehow connected to the long wavelength. So basically, this theory tells us that everything converts variable. So it's not very far from the long wavelength limit. So they all have a very fast convergence for different configurations. Okay. And this also shows how the propagator is converged to the long wavelength limit. So everything also converges very fast. So at the beginning, one say that it's not the same, but afterwards, already at A equal to 100, they are the classical model. I mean, of course, before the oscillation, after that, yeah. And finally, the interesting thing, of course, is the effective action. And this is much harder than the propagator because propagator we only need to compute one configuration. But for the effective action, we need to sum it over all possible configurations. So this can also be done numerically. Let's take some computational time. And it turns out it also converts very fast into some constant value for the effective when we have a fixed lattice. Which means all these things have a nice continuum limit, even when we don't consider the long wavelength. This is beyond the long wavelength approximation because we are summing over all possible configuration up to 10. But this is really all the things we obtain from theory at one loop. If we set at this level equal to this, so this is the possible. But we have a convergence. The difference between this for calculation and the previous long wavelength calculation is now. So this formula is very similar, but now we have a C, which is complex. In the previous calculation, long wavelength approximation C is real. So we get a real critical point. But in this for calculation, C is complex, and it turns out we have a complex critical point. We go to quantum equation. It has convergence, but now everything becomes complex. Which means we are really going to the quantum regime, classical. We have a complex critical point. Yeah, I think with that is the more or less conclusion of my talk. So what we have achieved is that we can show LQG is the UV finite if we use the coherent testing formulation and compare it to the standard quantum field. And we can also derive the effective description in the RR limit, which is our long wavelength approximation, and we prove that it's in classical system. And also we check the convergence of the short wavelength limit of the 4 quantum one loop effective action. Of course, there are more things need to be done. The first thing is this one is a coherent theory, but we use explicitly the matter field to write them as a gauge fixing thing. One idea is to remove the matter field to write everything as a covariance. So it's not rely on the Hamiltonian formulation, it's really the four covariant percentage. Another thing is we are dealing with flat background. Next step is of cosmological. But this, if we go to cosmological background, we cannot use fully complete. Background and we need to go to the Hit kernel formulation. I mean, Fourier transform a long time, not long time. So we need to go to the Hit kernel. And of course, the final thing is how to deal with a no-trivial regression. Yeah, that's all. Thank you very much.
And thank you, Professor Liu, for the wonderful talk. Very great timing. Any questions? Maybe let me ask you first a very naive question. Can we replace the dust with radiation? Does it make any sense?
With what radiation?
Any methods?
Yeah, we can do that. So that is, so basically, we can, for example, we can use electromagnetic field to do the decomposition as well. Based on the magnetic field to do the decomposition as well.